Hello there. Advanced Ecological Methods class. At this point, you should have covered the previous videos, which would have gotten you a good start on why we measure the spread of points around the mean as the variance and how that's related to the standard deviation by the square root. And what is a random variable, how to find the mean, and the fact that when you're looking at a normal distribution, 95% of the points will be within plus or minus 2 standard deviations of the mean. So they'll be within 2 standard deviations from the means. We talked about that. Now, let's move on to something slightly more practical here. We're getting closer to actual hypothesis testing, but we're going to work on the concept that is the confidence intervals. Ecologists often ask the question, does sample A or did sample A and sample B come from the same parent distribution? They ask this question because that's really the only one we can ask in a lot of ways, and it's rephrased as, what is the probability P that sample A and B came from the same parent distribution? This is something that we can calculate. I cannot tell exactly if let's just leave it at this. We can calculate the probability they came from the same parent distribution. We cannot calculate what parent distribution they did come from. We can only begin with the assumption of a parent distribution, like the one below, and ask, what's the probability that sample A and B came from it? So let's take a look at how that works. The parent distribution of individual points is drawn here. What I'm going to do as I go through this is highlight the areas that I'm speaking of. So there's our parent distribution, all right, of individual points. I wrote it out so it'd be a little faster for us all and neater. We know that it has a variance value here that is the width of the distribution, and you have the x bar value down here, which is the mean. What we're going to do is then take a sample from that parent distribution and look at the properties of some of these values. If we take a sample of n equals 5 things, now this is essentially a random sample from this distribution, all right? Of course, the mean, if we look at something like this group of numbers, x1 through x5, you can make a pretty good estimate that this mean, or the first sample mean, is going to be pretty close to the parent mean, right? It's going to be close to the parent x bar. It won't be exactly there, but it'll be near there. Closer than any one of these single points on average, the 1 through 5 samples, because those points could come from anywhere in the distribution. And what we're going to do is repeat that in your mind 100 different times, 100 times. So we'll take a sample of 5, calculate its mean, put it here. Take another sample of 5, calculate the mean. Calculate another sample of 5, calculate the mean. Now in ecology we don't actually do this, but we might conceptually do this as a thought experiment and collect up all of these x bars until we have 100 of them. And then let's take them and plot them in a histogram so that they look something like this drawing below. 100 means of n equals 5 might pile up into a shape that looks something like this one. Now as you've noticed, I've made this shape much narrower than the parent distribution shape. So the variance of these means is going to be narrower than the variance of the points of the parent distribution. So I'm going to put this in red. I'm going to compare this variance down here to this variance up here. When I compare those two things, we notice that the one at the bottom, these means has a narrower, smaller variance. And the reason for that is because each estimate of the mean, using 5 samples, is closer to the parent mean than would be a single random point, which is what the parent distribution is made of. So we know that, for example, the larger the sample size, and this is a sample size of n equals 5, the better the estimates of the means will be, and the narrower, the smaller the variance will be down here. So as n gets bigger, this thing, which is the variance of this mean, gets smaller. Now I'm going to say some notation things on here. I've gone ahead and used this notation for the variance of the mean. Now that is the variance of the means, and the notation has this small x down here that I don't want you to miss. It's x bar, in fact. So it represents the variance of the means. Now, in this case, we actually got the variance of the means by taking a bunch of means and calculating their variance. Kind of insane if you were doing actual ecology in the field, but we can do this using a thought experiment, desktop, computer example, all right? So this pattern is really important, and I've written a little paragraph to describe the relationship between these two things. It says, and this is actually the fundamentals of a thing called the central limit theorem, which we will be exploring, theorem, right? We will be exploring in 2 weeks from now. And the central limit says that when you take samples from a parent distribution and you calculate their mean and you find the mean of means, it says here that the mean of means is an unbiased estimate of the parent mean, which is why I have put it on exactly the same location as the parent mean on the graph. We also know that the means from any parent distribution will be normally distributed. So if you collect a bunch of them, they will be normally distributed. That is weird. We're going to explore that too. It is really weird, but it's true. It's a property of the mean. Even if the parent is shaped like a camel with a two-hump camel on the back, the means will still be normally distributed. The variance of the means is smaller than the parent variance by 1 over n. And there it is, the magic ratio right there, 1 over n, where n is the size of the sample used to calculate each mean. So n is the size of the sample. In our case, it was 5. And the variance of the means, therefore, which is this variance down here, and this variance, is equal to the variance of the parent distribution divided by n, the sample size used to calculate each mean. So that's pretty profound. What that means is that, and I'm gonna circle this little thing here. This is crazy. Woo! That means that the relationship between this number here and this number down here at the bottom is known. So if I were to write that out, it would say something like this, that the variance of the parent distribution is equal to the variance of the means. Whoops, sorry. Let's try this again. I would write it out and I would say the variance of the means is equal to the variance of the parent distribution divided by n. Now n is not 100 here. It's not the number of replications we did. It is the number of samples used to calculate each mean in this distribution of means at the bottom here. Now we can also reverse those numbers, and you could write, using your algebra, you could rearrange this equation to say that the variance of the parent distribution is equal to n times the variance of the means. So if you knew the variance of the means, you could calculate the variance of the parent distribution. So that's pretty nice. This is a powerful thing. That's as much as I'm going to say about it right now. Let's go and use it for something. And why is this useful? Let's go back to that original question. Did sample A and B come from the same parent distribution? What is the probability the two came from the same parent distribution? Let's go down and look at the next thing I've got written. It says, does the plus or minus 2 standard errors equals 95% still apply? And the answer to that question is yes. And I'm going to draw this right here. This distribution here, redrawn like this, I can still put right here in the middle is the x bar. And if I add 1 standard error and 2 standard errors, sorry, did I say it's standard errors? It means standard deviations. Minus 1 standard deviation and minus 1 standard deviation. These are still values that are making a normal distribution. And so this is minus 2 standard deviations. There we go. And because of that, we can still say that we have 95% of the points in this range, 2.5% out here, and 2.5% out here. Because it's a normal distribution, that still works. Now, keep in mind that these are actual means. The next question we ask is, since we're not really going to go collect 100 means out of our samples out there, we're going to have maybe 2 means that we have to compare. We'll ask this question of how can we estimate the standard deviation of means, or the variance of means, without actually having 100 means. So the variance of means is what we're interested in down here. So we don't have 100. One way of estimating the variance of means might be to use this equation that I just wrote up here a minute ago. We have these 2 equations, right? We know that we can get the variance of the means in the first equation if we have the variance of the parent distribution, and we can divide it by n. We also know that we can get the variance of the parent distribution if we have the variance of the means. But the first question, this is the information we really need at the upper part. All right, let's think about that for a sec. Can I get a good estimate of the parent distribution variance? What is my best estimate of the parent distribution variance? The best estimate would be coming from these numbers here. Notice that this little sample here actually provides me an estimate of the parent distribution variance. And it provides me that estimate in the form of this s squared, which is an estimate of the variance from a sample, an estimate of the parent distribution from a sample. So that is essentially just the variance formula divided by n minus 1. So we know we can use that. So if we take our simple sample of 5 things from just one, and from there we estimate the parent distribution variance. So what we can do, and I'm going to write that equation back down here, I'm going to write this equation that says the variance of the mean is equal to the parent distribution variance divided by n. I can estimate this from the sample, which is calculated as s squared is equal to the sum of I equals 1 to n of x bar minus xi squared divided by n minus 1, right? And I also know the size of my sample, which was 5, right? So if I have 2 samples of size 5, I can calculate the variance of the means. Now once I have the variance of means, which is this, I can use that variance of means to go right back to, I'm thinking about getting to here, right? So how can I find the range of 95% of mean values? And I need the standard deviation of means. So I should define something here, and that is to tell you that the square root of the variance of means means I'm going to rewrite that as the variance of means square root. Pretty obviously, it looks like this, right? And that number is actually equals the standard deviation of means. Well, you can kind of forget that term, I guess, because this term, although it was used back at the turn of the century, apparently a lot of people got confused by the standard deviation of means, because if they didn't finish their sentence, it was the same as the standard deviation. Notice, though, that this is the standard deviation of means, not the standard deviation of points, which are 2 very different measures. One, remember, the means are these the variance of these samples here, of the means, and the other was the variance of these points in the parent distribution, all right, which is just called the standard deviation. For that reason, people renamed this value. They got rid of this name, and they called it the standard error of the mean. The standard of the error is shortened SEM, okay, standard error of the mean. So that is what this term is, and it is found very readily by taking by calculating first the variance of means and then taking the square root. Therefore, what is the relationship between these numbers? So we can go back to our original sample. Our original sample was x1, x2, x3, x4, and x5. And from these we know we could calculate a variance, s squared, and we also have a mean. And so the mean is the best estimate of the parent mean, right? So we know that. But what about the and this is the best estimate of the variance of the parent. So if you wanted to know, from this point, we're going to solve then. That means that the variance of the means will be equal to s squared divided by n equals 5 in this case, which equals s squared over 5. So whatever that estimate is of the 5 points, the variance of the parent distribution estimate, we will then use that to calculate this variance of means. And that's the variance of means. I'll write it there. And now that I have the variance of means, what I will want to do is find the standard error of the means, which is the standard deviation of mean. Shh, quiet, secret, don't tell anyone. I'm just going to take the square root. Take the square root of the variance of the means, which will equal the standard deviation of the means. Now what we know is that 95% of means of size 5 taken from this parent distribution, I'll just say the same parent distribution, okay, just to make it easier, will be within I don't want to write will be within. In the interval, and the interval is the mean, which we calculated, of the sample, plus or minus 2 standard deviations of the mean, which is also written as the mean plus or minus 2 SEMs. So in that case, we've taken our data, right? We calculated, and what we've gone to then is this position here, which I will circle our happy end zone here, where we now have the mean, and we can calculate that there's a 95% chance that other means taken from the same parent distribution will fall in this range, because that is the 95% interval. This is called a confidence interval. This the 95% confidence interval. Okay, and specifically what that means is if 100 samples are drawn from the same parent distribution, (95% will have a mean value in this interval. Quite literally, 95% of the time, means of same size, n equals 5, taken from this parent distribution, the same parent distribution, will have a mean value in this interval, okay? And that interval is the mean plus or minus 2 standard errors of the mean. To get here, quick review, we began with a parent distribution. We manufactured these means out of it by randomly sampling them all, and then we went back and we plotted those means as a histogram, and we know that the actual standard deviation of those means produces one standard deviation is 66%, 2 standard deviations of the mean is 95%, so we know that those conditions still hold for this distribution, but this is a distribution of means, and in the field we don't have that distribution of means, but we do have an estimate of the parent distribution variance, and we take that sample down here from our parent distribution, and we use this rule of the central limit theorem that I've written out up here for you. We use this rule to show that the variance of the means will be equal to the parent divided by the sample size n. Very simple calculation. And then from that information, we can take the square root of that number to get the standard error of the mean, which probably should have been called the standard deviation of the means, but that term again lost favor and it's gone. So you might notice from this, though, that there's a little bit of a shortcut issue. I should look at this equation here, the variance of means. You can also figure out the standard error of the mean here. You may have noticed that if the variance of the means is equal to the variance of the parent divided by n, then you've also noted that if you take the square root of both sides of this equation, the standard deviation of means, or the standard error of the mean, is equal to the variance divided by the square root of n. And so this is why this is the equation for standard error of the mean, because it drops out all the unnecessary calculations using the variance. You can simply go straight to this, right? So when you get a sample, you calculate the standard deviation, and then you calculate the standard deviation over square root n when you want the SEM. I feel pretty good about that. This was a nice lecture. Thanks for listening. We are definitely going to apply this information in 2 weeks for the central limit.